calibrate our observations of velocity. And all this, of course, that in this case will be done using 3D simulations. So I first will give a small introduction about our method and some physics involved in it. And then I will talk about the 3D simulation that we have used and how we carry out the kinetic transfer, and then comment results and conclusions. So the main question that we want to address in this work is, what is the local frame of rest on the Sun? As you know, when you measure Doppler velocities from observations, you observe a spectral line, and you want to measure velocities using the spectral line, you need a reference. And those observations are usually affected by the rotation of the Earth, the radial velocity of the Earth around the Sun, and the rotation of the Sun itself. So, if we were located on the Sun and we want to measure a Doppler velocity, then we will use the normal Doppler relation, and we will get the velocity. But we are on the Earth, and from the Earth we have all these effects that I mentioned, but we also have the problem with the uncertainties in the atomic data. That is, we don't know very accurately what the wavelength of the line is in the laboratory, and that also causes errors in this relation when we convert from wavelengths to velocity. So usually the methods that people use, I'm sorry, this looks much better in my laptop. There are usually there are three main methods used to calibrate velocities. And the first one is, if we have a sunspot in our field of view, the magnetic field in the umbra suppresses convection. And we can assume that it's at rest. So then you can say, okay, the spectral line that is formed in the umbra should have a zero velocity. But this, of course, is assuming that the umbra is at rest. And yeah. So if you don't have a sunspot, of course, you cannot use this method. There's another way to do it. Is telluric lines are lines, oxygen lines forming the.
No, that destroys the thing. Wait. Not automatic.
Right. So telluric lines are lines forming the photosphere in the atmosphere of the Earth, and they are usually present in some spectral ranges. So if they are observed with the spectral line that we want to analyze, then one can use those to determine the wavelength scale in the Earth and convert it to the Sun using the ephemeris of the observation. But if you have an instrument that is filter-based, that is, you have to tune the instrument to get data, this is very expensive. And usually those lines are not present in every spectral range. So this is also a bit limited. Other method is to use the solar atlas. Someone actually observed with very high resolution the solar atlas and corrected the atlas for all these effects of rotation and rotation of the Sun. But this only works at solar day center, and it's also affected by uncertainties in atomic data. And the last one that someone proposed was to use a 3D simulation, and based on the 3D simulation, measure the convective blue shift of a line and use that to calibrate the observations. That is, if you know the input wavelength and you synthesize a spectrum, when you convert to from wavelength to velocity, you know the wavelength that was used to synthesize the line. So you're purely measuring the convective shift of the line. And you can compare that with your observation. And this is what we are doing. So basically what we do is use this approach and calibrate it for many lines.
So you're essentially assuming that the turbulence you see in your simulation is the turbulence in the sun.
Well, what we are assuming is basically that the statistical properties of our simulation are the same as in the sun.
Exactly which statistical properties? Say URMS, root mean square velocity, or
Well, I will come. That's exactly what I want to explain right now. So, one slide more. Well. So, some basic knowledge about this convective motions. So, I don't know how familiar you are with convective motions, but they have very strong. They leave strong fingerprints on spectral lines. And actually, if you think about the solar line, it's very hard to define the center of that line. There is no such a thing like the central wavelength. First, the lines are very asymmetric, and they have the bisector of these lines has a C shape. And this was discovered, well, explained by a Swedish researcher many years ago. And also, they are blue shifted. And it's usually around 300 kilometers at this center. Is it 300 meters per second, sorry. So this is a snapshot of a simulation, and I have, you cannot really see here, it's a bit weird the contrast, but there is a cross here.
Simulations are.
Huh?
Which is your simulation?
This is a simulation. It's not the one I used in this, but it has higher resolution than mine and it looks nicer. So I just have it here. It's a realistic simulation, nevertheless. So I have marked here a cross, and there's another one here that you cannot see, but it's in my. And so basically, this spectrum here, dashed, is the one in this cross. Comes from this cross. You can see that it's blue shifted compared to this one, that is darker and comes from the intergranular lane. Okay. The solid line is the total average of the field of view. So basically, when we compute spatial average of this model, we are creating we have a statistical average of bright blue shifted spectra with dark red shifted spectra. So there is a clear correlation. Bright is blue shifted, and dark is red shifted. And this produces a C-shaped bisector, and I will show you now. So this is the snapshot, and we start to average the spectra. Okay, so it's increasing the number of spectra average. And you can see this is the line profile as a function of the number of some spectra, and this is the bisector of the line. The bisector is this. It's basically the middle position at each height. So you can see that it's important to have a good statistical sample, and this is only for one snapshot. If you have oscillations, the whole snapshot goes up and down because it's very small. This is only 6 megameters. So then the whole bisector will also move. You will see this later in the plot.
So the minus 200 meters per second means what then?
Blue shifted.
Yeah.
Minus is blue in spectroscopy because it's.
Right.
But this is only one
The
snapshot.
simulations, of course. So we know that the simulation was moving.
Yeah, but this is only one snapshot. This is just to illustrate how the line changes when you change the sample.
Don't you want to subtract exactly that value later on?
Yeah, exactly.
Right.
But you want to determine what's that value.
Yeah.
so what you're plotting in that snapshot is actually the line of sight component of velocity.
No, this is just No, this is just intensity, continuum intensity.
Of the line.
Yeah, but it usually resamples also the velocity. Yeah, because of what I said. Bright is
Yes,
blue
exactly.
shifted, and yeah.
So the dashed line on the left, that's not where the maximum is. That's where the middle is, right?
This one.
It's the same line, right?
This is just to indicate the
Yes.
average
Yeah.
velocity of the bisector.
Yeah. So these are the two same values.
Yeah, this two.
Yes.
Yeah. It's just that this one is in wavelength scale and this one is in velocity scale.
Right.
So, just to clarify, the method is to take a 3D simulation, compute spectra with it, fit the line strength to reproduce the solar atlas, the observations basically, because these models are realistic up to a certain point of view, and we want to be able to reproduce the spectra. And also atomic data has some uncertainties. So we think that the strength of the line is a value, and it might be slightly off from reality. So we fit and hopefully compensate for those errors. And then we measure the convective shape of the lines for different heliocentric angles. And with that we can calibrate our observations. So this method relies that there is a quiet sun patch in our observations that we can use to determine the quiet sun average spectrum and compare with these simulations. So now we'll talk about the 3D models that we are using and how we do the radiative transfer, which is very simple. So we are using a 3D simulation of the photosphere. It's fully hydrodynamic, so it doesn't have any magnetic field in it. And this is one of the assumptions that we are doing. Quiet sun is really quiet. There is no real... The details of this simulation haven't been published by the author, but I think they are preparing a paper now, so maybe it will come.
Is this a new code or?
New code?
The hydrodynamics code, is it new one or it's based on design?
No, it's a new code.
What?
I mean, they have improved how the radiative transfer of energy is done in the simulation, but I don't know if they just modified the code they had, or if they are writing a new one.
I mean, it's the Stagger code, right? Which
I guess so.
Nordlund and Steiner have been using since the '98 paper.
But it's not Nordlund.
It's not?
No.
Not in
this is the Australian, right?
Yeah, but Trumpeduck is, of course, a former, I mean, has been, I thought, yeah, he's certainly working with him.
Okay, but then it's, I have no
He's
idea.
been working, of course, with, what's his name, from Uppsala, who was in Australia and is now in Munich.
Asplund?
Asplund, yeah.
Yeah. So we got this from one of
And
the
Asplund
students.
himself also uses these kind of simulations with a model code. Yeah.
Yeah. And well, the box represents a 6 megameters patch of the sun, which contains right now around 30 planets maybe. And it extends around a bit less than a megameter in depth. So it contains a photosphere and probably a very low chromosphere. And oscillations are present. And the role that they play in our profiles is that they broaden the profile slightly.
But only if you average about more than 4 or 5 minutes, right?
Hmm?
Only if you average about 5 minutes.
Yes, but the oscillations are also present in the observations. You have T modes, so you want to reproduce that. So,
Right.
and well, one.
Oh, but yeah, but the amplitude of the oscillation is actually not solar value.
The solar value is around 1 kilometer per second.
The reason it's known that it's too strong because it has to do with how big the simulation volume is.
Yeah. But anyway, it doesn't matter because when we're fitting the abundance, we are fitting the strength of the line and to reproduce the observation, and we account for the oscillations there. So if the oscillations were too strong,
Yes.
they would produce a way too broad profile, right?
Yeah.
But if then you compensate with the abundance,
Oh.
then you are reproducing a.
How do you do this? I mean, is that? I don't understand this. Do you understand this, Jan?
Yeah.
No, it won't be perfect, but it's sort of the best thing you can do.
Yeah.
I mean, how do you compensate for this by changing the valencies? You mean?
No,
No.
You don't do that.
No.
Yeah.
But you said something about abundances.
No, I'm just saying that we fit the abundance. We use the abundance as a free parameter on each line
Uh-huh.
to try to reproduce the observations, to get the best fit
Yeah.
of the observations. And of course, this is compensated for many things. But I think the authors have sort of proved that this, I'm not talking about fitting the abundance, but these models keep a very close profile to reality, usually.
Uh-huh. Yeah, but we already have a problem with the abundances.
Well, it depends if you want to interpret the abundance or not. I don't make any interpretation of the.
No, but now you're assuming that the abundances, of course, are correct.
No, that's a free parameter.
No, it's a free parameter.
That's the free parameter using to fit the observation.
And if you see how these studies work, the series of papers by Asplund, he fits the abundance for every line, and then he makes a statistical study of
Yeah.
how.
Yeah.
So each line has different abundance, determine abundance, and then they determine the, I think they do with, they classify the lines with.
Right, but I mean, from a helioseismological point of view,
Yes.
you would hope that something is wrong with that, of course. Right?
But I haven't said
because of
we're not at all determining abundances.
no.
So abundances are only a free parameter, or you can say that we are adjusting the oscillator strengths because they are also narrow. We're not sort of doing anything like we're not almost looking at the abundances. We're just
No.
trying to reproduce.
Yes, but I mean the question was, of course, ultimately whether the reason for this discrepancy with the abundances now could have to do with the fact that the oscillations in the simulations are overemphasized.
No, they should not, because the oscillations won't change the equivalent width.
Yeah.
I mean, they only broaden the profile, but it could be a source of error here, if because when we do that, when Hyman does this fit, he's not looking at the equivalent width, but fitting most of the line profiles. So it's a possible source of error here.
So
If the oscillations are too strong or something, but not the first order.
And so the reason is that this is a completely symmetric process, so they would not change the shape of the sea.
Yeah. I mean, the point both in simulation and observations is to average.
Okay.
Average for a sufficient long time and sufficient long space so that they go away and you just see the average of everything. That's a go.
Yeah. Thanks. Yeah.
So we use, in order to do the rate transfer, we use multi. It's called 3D, which is not really a 3D rate transfer code, and it doesn't really matter because we do LT computations in iron lines and a carbon line. And in order to do LT computations, you don't need 3D. You just set the populations by the local temperature. So there's no need for that. For the calcium infrared triplet, we also do the same computations. And in this case, we treat each pixel as a plane parallel on a sphere. So we use the 3D snapshot, but each pixel is decoupled from the others. And we assume plane parallel geometry to compute the populations with free quadrature and those. And well, the collisional broadening is kind of state of the art, the one proposed by Paul Backlund from Sona. And the atomic data was acquired from the VAL database. And one more comment about the oscillations, actually, is that one might think, okay, if we just include one period of the oscillations, we should have already a good average. But it turns out that the statistical sample of such a small box is not enough to describe this problem. I mean, you can see that only after adding a few periods is when the value of the mean bisector velocity stabilizes. So probably it's a very limited sample of granules and intergranular lines. You need some evolution to cover this. So we use the whole time series.
So collisional broadening, that means things like Stark effect and all these things?
No, it's a Van der Waals, right?
Van der Waals,
So, well, first thing is the results. This is what we produce. Let me explain what this is. Each of these couple of panels is a different spectral line. You see profiles. This is the center, mu 0.987. So this is basically going towards the limb as we go down. And these are the bisectors of each of these.
Okay. And the absolute shift is the actual one, yeah?
Yeah, the shift is, the thing is, we know the central wavelength that we use to compute the profiles. So now we can use that same wavelength to measure the convective shift.
Right.
It might be wrong, but it's the same. So we are just isolating the convective shift of the line in this case. And well, you will see that different lines have different behaviors towards the limb. In some, like the carbon line, it's a line that is formed very deep in the atmosphere. It's very sensitive to temperature. And it has completely different behavior than, I mean, this is almost 900 meters per second shift.
So the lowermost line is what kind of angle is that?
0.3.
So 30 degrees.
Yes,
0
yeah.
degrees? Sorry.
It's 35.
35 degrees.
2.3.
Is the maximum.
I don't think in terms of cosines. I don't know.
What?
I don't think in terms of cosines, but
Yeah. So 35 degrees roughly.
I think it's around that. Yeah.
No, not more.
But it's very close to the limb.
Yeah, but eventually you don't see anything, right? 0
Yeah.
degrees.
So I will just zoom in one of these plots to make it see more clear. Okay. So yeah, what you see basically is that it's then this center bisector has the usual C shape, but as we go towards the limb, the bisectors get more horizontal somehow, and always have a tendency to go to red compared to the center case. I mean, they are still blue, but in many cases, but they are going redder than the center case. And eventually they actually go slightly, in cases like this, for example, it actually goes a bit blue and then towards the red. So this is what we will call from now on the limb effect, okay? And we'll discuss this a bit. So the first thing we did was, okay, let's see what happens if we have observations and we have different spectral resolutions. What happens with our lines? Are they affected by the spectral resolution, the shift, and this type of things? So the first thing,
In the previous picture you saw already that the different spectral lines have completely different center to limb variation.
yes.
So which color has the strongest one then?
Which?
Which color? Red or blue? I mean, isn't that what it is? Towards red, it's maybe more stronger than towards.
Oh, I think it's just a trend. It usually goes slightly to the blue, but then it goes to red. And I think that depends on in which layer the line is formed, and
Yes.
and that's determined also by the atomic parameters of the line.
Okay, so it's not just a simple answer like this. Then.
Yeah.
Right.
So what we did is we convolve our profiles with a very simple treatment here. We just computed Gaussians of different full width at maximum and convolve our profiles with those Gaussians. And what you see is that as we decrease the spectral resolution, the line becomes less asymmetric, but the mean velocity of the bisector remains constant. What changes is, of course, because we are changing the symmetry of the line, is where the core is, which is this curve here. So if one naively uses the core of the line to determine the shift, you have to be very careful with this spectral resolution you have, because it may happen that you are doing it completely wrong. Now we go back to the limb effect. We tried to look on the literature for explanation for this effect, and there were some proposals, but they were never really thoroughly proved or anything. It was just like weak suggestions, like we think it might be this, and they didn't really try to explain what happened. We tried to actually get an explanation out of this, but these 3D models are very complicated, and there is, if you start to look in the models for example, in a situation like this where you have a granule, intergranular lane granule, this is just a slice of the model, it is not very clear that what's going on. And basically authors have explained that, well, when you go higher up in the atmosphere, this correlation between velocity and brightness changes and gives, that's what we know as reverse granulation.
That's what?
Reversed granulation.
Yes.
Or inverse granulation.
You mean if you go in the stably stratified part or what?
Yeah, exactly. Yeah. So in that case, at some point, the intergranular lanes have higher temperature than the granules.
Yeah.
That's in the upper photosphere. So, well, one might think, okay, if the line, when you want to go towards the limb, also,
Mm-hmm.
your change in effective height of formation of the line is usually formed higher. And that might change also. That will be explanation why the line goes to the red, because then that correlation has changed. Then, well, there were also some people that proposed that your line of sight is going through granules and intergranules, and somehow the redshift part is seen with a very bright background, and therefore that might be weighted with more weight than the blue side. But to be completely honest, if I try to make a picture of how that works, I just can't make too much sense out of it. And I think what they mean is that the line of sight, this is the, well, you can see it here. This is the, let me explain, this is the float. Sorry. This is temperature, float. Obviously bright is hot and dark is cool. This is the absorption coefficient at line core. This we can compute with a radial code, and this is computed for this line of sight. So all these properties are related to the line of sight, indicated by these rays. Okay, and this is the velocity, the line of sight component of the velocity through that line of sight. This value here is the formation height of the core of the line, and this one is the continuum formation height. Okay.
Yes.
So the whole line is formed basically in this range. And okay, so basically what one might expect is that since you have this reverse granulation, there is some corrugation of the tau surface in higher layers, and that basically systematically will give more surface to the red-shifted part of the granule compared to the blue-shifted. That was also proposed by Balthasar in 1985 with a very schematic picture of the granules and intergranular lanes. We also found that sometimes you have these hot columns in the intergranular lanes, and that systematically blocks the blue side of the granule.
The redshifted, I thought,
The blue-shifted.
but redshifted I thought you wanted to associate with the intergranular lane, which of course is opposite if it's in the upper part. Yeah.
Right?
Yes.
These are granules. Right. Now, if you start from the limb, this is intergranular lane, right? And this is red, blue, red, blue. If you start from this,
Yes. Right.
right? Now, where the continuum is formed, that is low in the photosphere, the tau surface is more like this. But if you go higher up, the tau surface is actually reversed. Okay? Yeah, so you can see this is red, and this has more area and a blue, potential blue side.
Yes, I see. Right.
So there are 4 effects, and it's not really clear what the weight of these effects, or what's the role of these effects in the final picture. And we couldn't really justify that one is more important than the others. However, we want to see it's clear that it's a projection effect somehow. And out of these 4 effects that mechanism that we are describing here, these three, the last three, are real 3D effects. That means it's really they are really influencing when you go towards the limb. They are breaking the symmetry of the problem in your projecting properties of the atmosphere in your line of sight. Whereas the first one, which is basically when you go higher up, it's not a 3D effect per se. It's just that you are changing the formation height and the properties of the atmosphere that are different. And this is a test that proves that. We took one of the lines. We said, okay, let's try to reproduce the limb effect, but instead of tilting the model, as we usually do to reproduce a limb, we just take each pixel and change the height scale, which would basically be what you do with a plane parallel atmosphere, right? And compare the bisectors with the real 3D case. And you can see that, well, yes, there is a small, I don't know if you can see here some marks, more marks. So the decenter case ends here, the next one ends here, and they go towards the red. So effect 1 clearly has some contribution to the redshift of the bisectors. But this limb effect is basically a contribution of probably these three here. But we couldn't really disentangle which one is the main contributor to this. It's probably some mixture of the three of them. What's that? The next thing that we did is, okay, what about the errors? How reliable is this? Are the simulations really realistic or not? So the first thing we saw is that some authors claim that LT is a wrong way to do iron lines. You should do non-LT treatment of the lines. That will actually, the consequences of doing non-LT will be to build up a very complicated atom model for the levels and carry out very expensive computations over the whole simulation, because it's a lot of snapshots and this takes time. So I think it would be impossible to do this right now in non-LT. But anyway, we said, okay, what happens if this was done in non-LT? What would be the difference? This author, they claim that in order to, the difference between, they measure abundances in non-LT. Is that the difference basically is that we have to decrease the abundance by 0.1 tex if you do it in LT compared to the non-LT. So there is a 0.1 tex discrepancy. So I said, okay, and they said that these non-LT departures are larger in the granules, which are formed higher in the atmosphere. So we said, okay, let's take one of these snapshots and let's divide it in granules and intergranular lanes based on the line of sight velocity and on the vertical velocity. And let's change the abundance of the granules and the intergranules and look for pairs that reproduce the line strength of the atlas. And then we see what the shift is. Because when you change the abundance of the granules and intergranular lanes, what you're basically doing is changing also the correlation between bright and blue and dark and red. So somehow the line must also change the shift. And what we found is this curve. So in this axis we have the abundance of the granule minus the abundance of the intergranular lanes index, difference between them.
What's X?
It's measure.
The fraction of the logarithm to base 10.
Yeah.
Ah, okay.
So the monster was given log. And this is the mean velocity of the bisector of those lines. So well, if you said, okay, if we take this 0.1, if we assume that all this discrepancy of 0.1 tex is due to differences in the granules, intergranular abundance, then the error that we will be doing will be around here, and it's less than 30. It's around 30 meters per second. So if we do a full non-LT treatment, we expect that the bisectors will be shifted by that amount, around that amount. The other test that we did is, okay, we are fitting the abundance for each line. Does it really change? When you change the abundance, are you really changing the location of the bisector? Are you moving the line by changing the abundance? And that's what we did here. So we took an iron line, and computed the profile for different values of the abundance, and then integrated the bisector, and that's what we plot here. The velocity of the bisector as a function of the abundance of the line. And this for 3 heliocentric angles, because towards the limb maybe it might be larger, the effect. And it's always, well, in the range that we are usually moving, usually also plus minus 40, 50 meters per second. So we estimate that our computations are correct within 50 meters per second, which is fairly good for this type of studies. Mind you, in granulation, typical values of the lines can be shifted up to 4,000 meters per second. So we think it's a solid result. And well, last, as a test of realism, we compared the bisectors of our simulation with the bisectors of a solar atlas. And that's what you see here. So we did it for the iron lines. And you see each of the iron lines that we have computed. The solid line is our simulation, and the dashed one is the solar atlas. You see that there is always a slight shift of the line, which is actually around 50 meters per second. But is that bad? Is that a bad result? Well, mind you, the solar atlas had to be calibrated. And there are authors that claim that these lines show dispersion of around actually 50 meters per second in the atlas. They claim that if you compare the lines of the atlas compared to the central wavelength, they made a comparison and they found that the lines are off by had a dispersion of 50 meters per second. I don't remember exactly how they did it. On top of that, in order to compute the bisector of the solar atlas, we assume a value for the central wavelength, as I said in the beginning, which might be wrong. We know, for example, our carbon line, the central wavelength is uncertain up to 1,000 meters per second. And we're trying to measure here things that are much lower than that. So, well, this is a very this is a great, for me it's a good result, I think. It's a realistic result. And the other result that you can check is that the shape is also fairly well reproduced. So we took then an example case. This is a dataset taken with CRISP, with the SST. And where we said, okay, now we will take real observations and try to calibrate the velocity for them. So the problem with CRISP is that, well, it's not a problem. FPIs, in general, parameter parameters, they have they have a surface that has small variations, and that produces cavity errors. In our case, those cavity errors appear as a pixel-to-pixel shift of the line.
What kind of things? It cause what?
Cavity errors.
Yes, and then you don't know this or not?
No.
What?
Well, I think you can.
I mean, it's two parallel plates with a higher reflectivity coefficient inside, so you get multiple interference. Okay. And if you have a small change in the cavity separation, and that comes primarily from the inhomogeneities in the coating itself, because the coating is in the order of a micron thick, and the accumulated errors in the coating thickness can easily be a transform of nanometers. And because of the interference caused by many reflections, you add up or accumulate phase errors.
Yes.
Yeah.
And then how do you...
It gives you wavelength shifts,
Yes.
which are local. These are probably raw instruments are placed close to the focal plane.
Yes.
To allow good image quality, and then this leads to wavelength shifts which vary over the field of view of the equation.
So how do you spell this?
Cavity error.
Cavity error.
You mean this comes
So basically,
I thought it was a
Cavity
Spanish
is
word.
this comes from the error in the coding of the fabricator,
Yeah, mostly.
and that's kind of random.
It's sort of random. I mean, there are large-scale errors, which because even though the coatings are applied to codes, they lead to a slight stress on the surface of the glass when they shrink somewhat. And so there are some large-scale errors from that, and then there are small scale errors which are on the order of atomic thicknesses from nanometers. Which occur on length scales on the order of a millimeter or so, typically.
but basically the problem is that it's not well a problem. The effect is that on each pixel we have small shape of line, and if you just take the average of this, you are effectively plotting the line because the profile has been shifted randomly to the field of view. So what we did is we arranged all the spectral points in one large array, accounting for this. I mean, we measure the cavity error, so we can actually know what the shift is. So we correct for the cavity error, arrange all the pixels, all these observations in one large array, and then we fitted all the points to a curve, and we take that as the average spectrum. And well, I did this with these square fits.
The cavity errors can be measured by giving a known wavelength.
Well, the cavity errors you can measure if you assume that what goes to each pixel is the same and known, you can measure the shift, right?
Right.
So we take even on flat field data, you assume that you have some kind of average spectrum, and you can measure the variation of the location of this, the core of this line. Basically, you can just measure the core of the line, and you will see that it's moving.
You take many frames while moving the telescope rapidly around sometimes, for example. So you smear out all the granulation factor, and the number of frames you use maybe 1,000 or more. In this way, you get in each pixel effectively the same spectrum, which is sort of average over the throughout each sample.
Absolutely.
And then you know that the spectrum in each pixel should be the same. And by measuring the deviations from
You
that,
know the cavity
you
error.
can map up the competence.
So that's what is here. Each of these clouds, I mean, originally we wanted to observe on a point in the center of this cloud, but due to the cavity errors, we get the dispersion on the x-axis. The dispersion on the y-axis is due to the granulation itself, because we have granulation in our image, and that gives you intensity fluctuations. So that's why we fit this profile, and this is our observed bisector, and the other one, dash one, is our simulation combined with the instrumental profile, with a theoretical instrumental profile. So we have used this to calibrate the shift of the line, and seems to work. The image that we get is consistent, but this is anyway 200 meters per second. As I said, the typical granulation RMS is around 2000 maybe meters per second. So small offset basically. So now we go to the conclusions, and well, it's very easy to summarize this. We have calibrated the shift of 11 nines using a 3D simulation, and this method should be unaffected by atomic uncertainties. And well, since we have fitted for to reproduce the observations, we are partially compensated also for errors in the line strands and things like that. And well, we have estimated an error of 50 meters per second. So,
Mm-hmm.
So this method is based on averaging over
the whole image or subfields of the
Yes,
image?
you should. I mean, as I said before, you need a patch at least of quiet sun on your image, and as quiet as possible. For example, in the image that I showed in the beginning of a sunspot,
I haven't asked the question yet. So it's based on averaging. So therefore it should be insensitive to scattered light on a short spatial scale. But if you have scattered light on a longer spatial scale, so you get mixing from different view angles, does that affect anything? Or is it insignificant?
you mean? Okay, I'm a little confused. You mean that you have an image of the sun, you're getting light from the lip of the sun into your.
For example, that should be darker, but maybe the other way around, that you're measuring things that
On the
you
lip.
get component from the center.
I think we're assuming that.
In principle, yes, but sort of expect that would be small. At least that's our experience from doing other observations. That I mean, but if you're very close to the limb, yes. But wisely, Jaime can look at viewpoint 1.3. So we don't publish anything very close, very close to the limb.
But the reason for that is also the models. The method that we're using to slant the model, at some point it becomes unreliable. So you know, you're assuming that you can shift the layers of a one snapshot, assuming periodic boundary conditions, and change the height scale. So basically, you're slanting the model that way. And but we haven't tested. I haven't tested if that has a limited range of validity or anything. But there's another thing I wanted to mention regarding your question. You said you should use a patch of white sun on your image. As I said, there are P modes in observations usually, and you should make therefore you should make some kind of temporal average also to make sure that you don't have a suddenly a patch of that is 1,000 meters per second shifted.
So this 50 meters per second sounds huge to me.
Because that in the amplitude of P modes could be 1,000 meters per second in sticks in the book.
Yeah,
so
sure, but of course, because we know that with the Hubble instrument, one is down to 40, 50 centimeters per second, right? With the accuracy at least of the, and I thought of the average position of the star, the average proper motion of the star, because out of this you of course find whether the sun or the star has planets. So if even for the sun with the best instruments you have only 50 meters per second, it's like a factor of 1,000.
Yeah.
So you mean that you can measure variations?
But those are relative measurements.
Yeah, right. Yes, exactly.
Here we're interested in the absolute.
I think Danish Swammers long time ago pointed out that you can like these extremely accurate measurement, but if you don't know the convective blue shift, you have huge errors in terms of absolute velocity. So I'm quite certain that.
But of course, if you have I mean, with these stars that are far away, you know they come and go to you, right? So there could be, of course, some absolute motion away from that solar system, away from us. But apart from that, you should be getting an extremely accurate measurement of even an absolute value with respect to the position of that other solar system, which you could perhaps.
Well, there is another thing is that you can have a laboratory reference on those observations, right? You can have a reference here that is very possible, right, to get that.
Oh, that even if you have that, when you convert to the frame of rest of the sun, and you convert from wavelength to velocity, you have to assume a line, central wavelength. If that line has 1,000 meters per second as a carbon line uncertainty, you can be completely off.
Yeah, that's like I'm talking about references like a telluric or...
Yeah, well, how do you convert with a reference like a telluric?
So with this method you can kind of recalibrate all your data you had observed before, or
No, okay, the point is, there are studies when you need very accurate velocity. You don't have to do this with all your data.
Yeah, sure.
But imagine that you're trying to measure if there is convection somewhere. You want to measure you really want to know if something is going up or down. Then you need an absolute prediction. For example, if you're just trying to measure, I don't know, if you're not measuring velocities, you're measuring magnetic fields. It doesn't matter if there is an offset in your velocity calibration, because then the magnitude of the magnetic field will be the same. So this is purely for studies that require that we know if something is moving up or down. It's more like that, and if that amount is small. If what you're trying to measure is, for example, is much larger than the convective shift of the line, probably won't matter, because it will still go up or down. If you're trying to measure something that is, I don't know, 10 kilometers per second, the velocity is 10 kilometers per second, like some atmospheric stuff are reported now to have 30 kilometers per second velocity in H alpha and calcium. Whether you have an error of 200 meters per second, doesn't really matter.
So it's like really important when you want to measure the right flows in sunspots,
For example.
and want to compare it with simulations.
And probably you want to, if you are trying to exactly model what's going on, then you need to know if it's going up or down.
And are there like other people also have done it, or are you kind of the first who had like the idea? And
Well, no, the idea came from one of our collaborators is Mats Karlsson from Oslo, and one of his students he was measuring also velocities, and for this carbon line they found out that the uncertainty on the wavelength, on the laboratory wavelength, was too large. So then they said, okay, for this line we will just take a simulation and measure the convective blue shift. And so we took the idea from them, basically. So they are the first that I know that used that, but they didn't calibrate for many lines or anything. Just took for their observation and took a simulation and computed this. So that's where the idea came from. But there is a lot of work also testing if the models are actually, if what we have assumed is valid. And so that's all this error treatment that we try to do a bit, and these tests that we carried out.
So the lines that are used for velocity measurement, are they all insensitive to the magnetic fields?
No, definitely not. The 6302 is actually very sensitive, right?
Then you will have a lot of pollution in a sunspot, right? Then it's not possible to measure, separate the field, and then you have to measure the magnetic field by a different method, and then use some physics to subtract out the magnetic contribution.
There are lines like the 5576 line, which are not magnetically sensitive at all. But also magnetic lines can be used because people often use inversion techniques where you actually fit the magnetic field vector and the velocity field simultaneously. And in this way you can get an accurate velocity out because you simultaneously fit the magnetic field and even the velocity gradient. So in that way you get flow. But if you're only interested in the velocity, then it is better to use a non-magnetic line.
Still, with the velocity difference, as the sun goes around during the seasonal variation, that velocity change is extremely small, right, compared to this 50 meters per second. It's much smaller, right?
No.
It's not?
No, it's,
I don't know the numbers.
what it is, but I think it's marginal.
Aha.
And anyway, the Solar Atlas they have removed all these effects, so it should be actually corrected for
right.
radial velocity and the daily variation also. The small rotation in that case doesn't play any role because we are observing at this center.
Yes.
You don't have the rotation at the center.
Yeah.
So like for you would be like now like a step to take. I mean there are people like have observed sunspot and really measure accurate the velocities there. and then like you use your method and then you can see
I guess that's the idea.
Yeah.
But I haven't worked with sunspots, so.
So if you measure the left and right limb,
Yes.
then you see a difference, right?
Yes. But it's purely induced by the. I mean, that's not on the. It's not on the gas. It's just a.
It's a shift.
Yeah, it's a shift.
Oh, a shift, yes.
So. Yeah, but you will find all those problems with this method because you just set the reference where this calculation totally.
But wouldn't that somehow give the relative velocity already somehow? Yes. I mean the absolute value somehow I was thinking just
I mean, if you observe two limbs, well, you cannot. If you cannot find the.
What?
Different regions.
I mean, I'm thinking, what?
I don't think that would have been anyway. But it can be an interesting exercise. Measure the rotation of the sun.
Which is unknown.
It was first done in Uppsala, by the way. Measuring the rotation of the sun via spectroscopic methods.
Yeah, right. And that gives you this 452 nanohertz, right? Which
Sure.
It should, you said. Is that what you said?
Yeah, sure. You know that.
Yeah, because of course that was a puzzle, because in helioseismology the lowest value or the surface value that was obtained in the beginning was 462 nanohertz. There was this difference, 10 nanohertz, and there was thought to be some discrepancy, and only in the last 8 years it became clear that it's actually correct, and there's really a very sharp drop of the angular velocity towards the surface, which is called the near surface shear layer. So this disagreement was actually solar physics related.
Completely. That's completely out of my range.
Because it sounded that there was some calibration error, but it wasn't, of course.
No more questions?
Should we thank him again? Maybe like should we like meet